Section 4.5, derivatives and the shape of a graph. In this section, we're going to focus on how the first and the second derivative impact the shape of graphs. We're going to start by discussing how the first derivative impacts the trends of our functions. Recall that the derivative represents the instantaneous rate of change of our function f of x. So if f prime of x is positive for all x on an interval I, then f of x is increasing on that interval. On the other hand, if f prime of x is less than 0 for all x on the interval I, then f of x is decreasing on the interval I. So the sign of the derivative dictates the trend of our function. Whenever our derivative is positive, our function is increasing. Whenever our derivative is negative, the function is decreasing. Taking a look at the graph below, we're going to let f of x be defined by this graph. The first question is, where are the critical numbers of f of x? Recall from when we define critical numbers are any values in the domain of the function f of x that make the derivative of f of x 0 or undefined. As indicated on the graph, we see that at a, our derivative is undefined, which is indicated by the sharp corner, while at b, c, and d, the derivative will be 0, as indicated by the horizontal tangent lines. So in total, there are 4 critical numbers, a, b, c, and d. Next, we want to determine where f prime of x is positive. Wherever f prime of x is positive, that is where the function f of x is increasing. Scanning left to right, we can see the first interval would be from negative infinity to a, then from b to c, and then finally c to d. Next, we're going to determine where the derivative is negative. That means we're looking for where the function is decreasing. The first location where a function is decreasing would be from a to b. The second location would be from d to infinity. So based on the trend of the function f of x, we are able to determine where our derivative would be positive or negative without actually finding the derivative. Now we're going to talk about the concavity of a function. Concavity refers to how a graph of f of x bends. If a graph bends upwards, creating an effect that looks like a bowl that's trying to hold water, we say that the graph is concave up. To the right, we can see what a graph being concave up looks like. You can see how it looks like part of an upright bowl. What causes a graph to be concave up is when the instantaneous rate of change of the function, that being f prime, is increasing. If the function was increasing to begin with, meaning our derivative was positive, then as the derivative increases, it's just getting larger and larger, causing our graph to look like it's becoming steeper and steeper. However, if our function was decreasing, meaning our derivative was negative, then the fact that the derivative is increasing would cause our derivative to get closer and closer to 0, which creates a less steep graph as we trace from left to right, creating a concave up shape. On the other hand, if a graph bends downwards, looking like a bowl that is dumping water, then we say the graph is concave down. Looking at the figure on the right, we can see what concave down looks like, looking like half of bowls that are dumping water. The concave down shape is created when f prime is decreasing, meaning the instantaneous rate of change of our function is decreasing. As for the shapes, if our function was already decreasing, then our derivative is negative, meaning our derivative being negative and decreasing makes the derivative more and more negative, causing it to get farther and farther away from 0. And that's going to cause the graph to become steeper and steeper. On the other hand, if the function was increasing, meaning the derivative is positive, since our derivative is decreasing, our derivative is getting closer and closer to 0, causing our graph to look more and more horizontal. Some graphs may have a change in concavity. A point on the graph of f where the concavity changes is referred to as an inflection point. Now, how exactly do we test for concavity? We'll let f be a function that is twice differentiable over an interval I. If f double prime of x is greater than 0 for all x and I, then f will be concave up over I. On the other hand, if f double prime of x is less than 0 for all x and I, then f is concave down over the interval I. So similar to how the sign of the first derivative tells us where a function is increasing or decreasing, the sign of the second derivative tells us where the function is concave up or concave down. The reason why we're looking at the second derivative is because the second derivative is the first derivative of the first derivative. So wherever f double prime is positive, f prime is increasing, which means the function f is concave up. Whereas whenever the second derivative is negative, the first derivative is decreasing, which means the function f is concave down. So to summarize how to figure out where a function is increasing, decreasing, concave up, concave down, locations of local extreme or inflection points, we're constructing sign charts for the appropriate derivative. If we are asked to find where f of x is increasing or decreasing, or where f of x has local extrema, we want to make a sign chart for f prime of x. Recall, intervals where f prime will be positive indicate the function is increasing. Intervals where the derivative is negative, f of x is decreasing. Any critical numbers where there's a change in signs will be local extrema. If the sign change of our derivative is from positive to negative, that critical number is the location of a local maximum. Whereas if the sign change is from negative to positive, that'll be the location of a local minimum. If we're asked to find where our function f of x is concave up or concave down, or where f of x has an inflection point, we will make a sign chart for f double prime of x. The intervals where f double prime of x is positive is where f of x is concave up, whereas the intervals where f double prime of x is less than 0, the function will be concave down. As for the inflection points, any partition numbers of f double prime of x that are in the domain of f, where the sign of our second derivative either changes from positive to negative or negative to positive, will be the location of an inflection point of f. We do not classify inflection points based on the sign changing from positive to negative or negative to positive. Now we're going to answer the following questions about f of x equals x to the fourth minus 25x squared plus 12. First, we want to figure out where f is increasing. As we discussed in the summary, to figure out where f is increasing, we want to find where f prime is positive. So we'll start by finding f prime of x, which would be 4x cubed minus 50x. To help us determine where f prime of x is positive, we're going to construct our sign chart for f prime. We'll start by finding our partition numbers. First, by seeing where f prime of x is undefined. Since f of x is a polynomial, and polynomials are differentiable everywhere, then f prime of x will not be undefined. So next we'll see where f prime of x is 0. So we want to solve the equation 4x cubed minus 50x equals 0. Factor out 2x. 2x squared minus 25 cannot be factored any farther. Set each factor equal to 0. If we solve 2x equals 0, divide by 2 and get x equals 0. For the 2x squared minus 25 equals 0, add 25, divide by 2, and then square root. We get x equals plus or minus 5 over root 2, which is 5 root 2 over 2. So in total, we have 3 partition numbers to put on our sign chart for f prime of x. Now we'll construct our number line with our partition numbers. To help us determine what sample numbers to use, it does help to approximate the 5 root 2 over 2. 5 root 2 over 2 is approximately 3.5, while negative 5 root 2 over 2 is approximately negative 3.5. As we take our sample numbers one at a time, plugging it into f prime, we get that the signs from left to right are negative, positive, negative, positive. So to answer the question, where is f increasing, we can see from the sign chart of f prime, it is going to be increasing on the intervals where our derivative is positive, which would be negative 5 root 2 over 2 to 0, union 5 root 2 over 2 to infinity. The next question is, on what intervals is f decreasing? Which means we're trying to see where our first derivative is negative. Fortunately for us, we already still have the sign chart for f prime of x from when we tried to determine where it was increasing. This time, our answer would be the intervals where f prime of x is negative. And those would be negative infinity to 5 root 2 over 2, union 0 to 5 root 2 over 2. Next, we're going to determine where f has a local maximum and what the local maximum values are. To find our local maximums, we have to determine where our function is changing from increasing to decreasing, which means we're trying to find the critical numbers where our derivative changes from positive to negative. So once again, we can look to our sign chart for that answer. Keep in mind, it's not enough to just look for the changes in the signs of our derivatives. We also have to make sure our partition numbers are critical numbers as well. Checking all 3 of our partition numbers, we can see that they are indeed in the domain of f of x, since f of x is a polynomial. So indeed, all 3 partition numbers are critical numbers. As for the only critical number where we see a change from positive to negative, that would be at x equals 0. As for the value, that would be f of 0, where we plug 0 into the original function, which means the local maximum value of our function is 12. So next, we're going to find where f of x has a local minimum and what the local minimums are. Once again, we'll turn our attention to the sign chart of f prime. We already know where our critical numbers are, and we can see at negative 5 root 2 over 2 and 5 root 2 over 2, our derivative changes from negative to positive. So our local minimums would occur at both 5 root 2 over 2 and negative 5 root 2 over 2. As for the local minimum values, if we plug both 5 root 2 over 2 and negative 5 root 2 over 2 into our function, we get negative 577 over 4. So notice how all of the first 4 questions were answered through the exact same amount of work. So despite being 4 different questions, it's only one process to figure out the answer to all 4. Next, we'll determine on what interval is f concave up, concave down, and where the inflection points are. To answer this question, we have to look at the second derivative. The second derivative of our function would be the derivative of the first derivative, which is 12x squared minus 50. So to answer the last 3 questions, we're going to construct a sign chart in the exact same fashion we did to answer the first 4 questions. The only difference is we're now looking at the second derivative. So we want to see where f double prime of x is undefined or 0 to figure out what our partition numbers will be. Again, f double prime of x is a polynomial, so f double prime of x will never be undefined. As for f double prime of x equals 0, we need to solve the equation 12x squared minus 50 equals 0. Since it's a simple quadratic equation, we can solve this by adding over 50, dividing by 12, and taking the square root of both sides. And we get x equals plus or minus root 50 over 12, which would simplify and rationalize to 5 root 6 over 6. So f double prime has 2 partition numbers that we need to plot on a sign chart. So plotting our 2 partition numbers, this time we will take sample numbers and plug it into our second derivative. If you need to, you can approximate the 5 root 6 over 6, just like how we approximated the 5 root 2 over 2. When you pick your sample numbers and plug them in to your second derivative, our sign chart from left to right would be positive, negative, and then positive. Now to answer our last 3 questions. Where is f concave up? F will be concave up, where our second derivative is positive. It'll be concave up on the interval negative infinity to negative 5 root 6 over 6, and 5 root 6 over 6 to infinity. As for concave down, that will be where our second derivative is negative, which will be negative 5 root 6 over 6 to 5 root 6 over 6. Lastly, we'll answer the inflection points. The inflection points are where the concavity changes. Now keep in mind, to be an inflection point, you do have to be in the domain of f of x. That is because the inflection points are points on the graph of f of x. Both of our partition numbers for the second derivative are in the domain of f of x. Since f of x is a polynomial, So we'll have two inflection points. The x-coordinates of our inflection points would be negative 5 root 6 over 6 and 5 root 6 over 6. As for the y component, we'll obtain those by plugging the negative 5 root 6 over 6 and 5 root 6 over 6 into the original function f of x. And both of them would have a y component of negative 2,693 over 36. So keep in mind that even though there were 7 questions in total, all 7 of them could be answered with 2 sign charts. The first 4 questions could be answered with the sign chart for f prime, while the last 3 were answered with the sign chart of f double prime. Concavity can also be used to help us find the location of local min and maximums. This is referred to as the second derivative test. Suppose f prime of c equals 0 and f double prime is continuous over an interval containing c. If f double prime of c is positive, then f has a local minimum at c. The reason why this is true is when f double prime is positive, that means our function is concave up, which would cause our value c to be located at a minimum value. On the other hand, if f double prime of c is negative, then our function has a local maximum at x equals c. This is because wherever our second derivative is negative, our function is concave down, meaning c would be the location of a maximum. There is one problem with the second derivative test. That is, if f double prime of c is 0, the test is inconclusive. The reason why this is the case is if we consider the functions x cubed, x to the fourth, and negative x to the fourth. Their derivatives will be 0 at 0, but their second derivatives would also be 0 at 0. However, f does not have local extrema, g of x does have a local minimum, while h of x has a local maximum. So we have 3 different functions where both the derivative at 0 and the second derivative at 0 are both 0, but they have different behaviors at x equals 0. So we cannot draw any conclusions when f double prime of c is 0. Now we're going to use the second derivative test to locate the extrema of f of x equals x to the fifth minus 5x cubed. Since we want to use the second derivative test, let's find the first and the second derivative first. The first derivative is 5x to the fourth minus 15x squared, while f double prime of x is 20x cubed minus 30x. Keep in mind, since our function is a polynomial, our first derivative will never be undefined. So our only critical numbers, which are the candidates for our local extrema, can only come from when our first derivative is 0. Notice that because of the conditions of the second derivative test, we cannot use the second derivative test for critical numbers that make our derivative undefined. It is very specific that we can only apply the second derivative test on critical numbers that make our derivative 0. To find where our derivative is 0, we're going to solve the equation 5x to the fourth minus 15x squared equals 0. And we get x equals 0 and plus or minus root 3. Now that we found our critical numbers, to apply our second derivative test, we're going to plug each of our critical numbers that make our derivative 0 into our second derivative. And we get f double prime of root 3 is 30 root 3, f double prime of 0 is 0, and f double prime of negative root 3 is negative 30 root 3. So our function f of x will have a local maximum at x equals negative root 3 and a local minimum at x equals root 3 thanks to the second derivative test. The issue, because our second derivative at 0 is 0, the second derivative test would be inconclusive at x equals 0. When it's inconclusive, we could then go to the first derivative test, making a sign chart for f prime of x. We only need to check the intervals that are surrounding 0. So for example, I would only consider the intervals negative root 3 over 3 to 0 and 0 to root 3. If you pick sample numbers, you do get that our first derivative is negative on both sides of 0. So 0 would not be a location of a local extrema. But again, we only know this because the first derivative test tells us this. Just because the second derivative test is inclusive, that does not mean we can conclude that x equals 0 was not the location of a min or max.